Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think we should get started. Today we have Liang Wang from the University of Pennsylvania talking to us. Liang is a graduate student working with Professor Joshi. Last year, Liang gave us a very interesting talk on efficient algorithms for extracting the k-best parses from a parse forest. And today he's going to talk to us about faster decoding for syntax-based machine translation.
Thank you, Bob. This is a joint work with David Chiang at ISI. And so a little bit background. So machine translation, we all know, is the one of the earliest and hardest problem in AI. And some people claim it's AI complete, meaning if you can solve MMT, then you might as well be able to solve other problems. But what's the current status? Let's take the best available commercial software and input an English sentence and let it translate into another language and then back into English. And if you did this for Japanese, you get this. It's not that bad. And Spanish, the echo instead of the spirit. And the Russian.
That's good.
The
last one looks a bit so.
Okay, so back to our technical stuff. So the focus of recent years in our research community for machine translation is statistical methods. So basically, we have at least two modules. One is the translation model, which captures the competency or adequacy between the two languages. And there's a separate language model, which only captures the fluency of the output. So a high-level architecture is that you input a Spanish sentence, que hamble tengo yo, and if you just use translation model, it would produce a set of candidates, which is probably broken English, and then the language model comes in to pick the best or most fluent sentence according to the language model score. So you got I'm so hungry, which is perfect. This is all done by statistical analysis on the data. So for language model, we usually use an n-gram model, which is the standard technique now, and for our experiments, a trigram. So it can detect good English versus bad English. And for the translation model, which is more interesting, it trained on the bilingual text, and its job is to match input to output piece by piece. So the piece can be either a word or phrase or a syntactic kind of substructure. So word-based, you have a kind of dictionary kind of thing, and phrasal table for phrase-based. And for syntax-based, you have variables like x and y here, which correspond to constituents or subphrases. So this means in English, a passive voice is was somehow by somebody, but in Chinese we say by somebody somehow, so there's a swapping between the two constituents. And here, put something on, in Spanish, poner x. So these x and y meaning variables, and so these rules can have better generalization ability, and it can capture long distance like was by dependencies. And that is the focus of our talk. So the previous is just a high-level architecture. Nobody really want to first produce broken English and then perfect English. So what we really want is a one-shot joint decoder, which is language model integrated decoder, that like a black box. So just give it a sentence and output the perfect English. But this is actually being observed to be computationally challenging task, and especially when you have a syntax-based model for translation model and n-gram language model. Why? Because syntax-based translation model, there is a hierarchically branching structure like a context-free grammar, so you have trees. And here for language model, you have a linear sequence like a like a finite state machine. So the two machineries are very different, and it's the interaction between these two very different machineries, the context-free machinery and the finite state machinery, that is causing the problem to be very expensive computationally. And that is the problem that we're going to address in this talk to develop better more efficient algorithms to search this complicated space more efficiently. So that is our objective, and this is the outline. So we're going to look at more detailed level the problem why translation with an n-gram model with syntax-based translation model is that hard. We're going to do some more detailed analysis, and then we present two techniques, cube pruning and lazy cube pruning, that efficiently search over this complicated space and then experimental results. Any questions? Okay, so to do translation with syntax-based models, people usually have a synchronous grammar. It's because one grammar, like context-free grammar, generates one language, and when you have two languages or even more, you must have a grammar that have two dimensions. So it generates, like synchronous grammar, generates pairs of strings or pairs of trees simultaneously. So for example, if you're translating from Chinese to English, you have Chinese 鲍威尔与沙龙举行了会谈 with English, Powell had a meeting with Sharon, and you can have this kind of synchronous grammar. The first rule says at the top level, the word order is the same between the two languages, basically a subject and the verb phrase. But when you rewrite this verb phrase as one unit, so this VP corresponds to this is called co-index non-terminal, then there is a syntactical reordering. So basically the PP and VP are swapped between the two languages. So this rule means they are swapped, right? And this rule says the Powell corresponds to the Chinese transliteration of the English name Powell, that is 鲍威尔. So basically you can have this synchronous trees, that is a pair of trees based on this synchronous context-free grammar. Now, if you have a synchronous CFG for the translation model part, again, we're going to see that using the translation model only to do the translation, or called decoding in MT literature, is really easy. So why? Because if you have a synchronous grammar and you have an input sentence, like 鲍威尔与沙龙举行了会谈 in one translated into English, and you start with this synchronous grammar, what do? You basically just parse the input sentence using the Chinese part of this grammar, right? So let's suppose there's only the Chinese part, Chinese projection, and this is actually a Chinese grammar. Use this grammar to parse this sentence, and you get, so this part is a PP, this part is VP, and you can combine this PP with VP to form a bigger VP, and then you can combine MP VP to get an S. So this is just like a monolingual parsing. But to do translation, you have to recover, this is the scores, so that you always prefer the smaller number, or this is like a cost. But to do translation, you need the other dimension, that is the output, that is the English part of each corresponding rule. So to do translation, the only additional task is to remember the English substrings for the subtrees that you just built. So basically, 与沙龙 gets with Sharon, and 举行了会谈 gets held a talk. Then when you combine this PP with this VP to form this bigger VP, you use this rule that reorders, that swaps the word order, so you get held a talk with Sharon for this Chinese subphrase, right? So basically, it's just like monolingual parsing, but building the corresponding translation, sub-translations in the same time. Then you get the full translation when you combine Powell with held a talk with Sharon. So this is how you do translation using synchronous CFGs. Is that clear? Okay. But so we already know that this is easy. But when you have an n-gram model for language model, and combining them in one shot, language model integrated decoding, I said it's hard, and we're gonna see why it's hard. So this is just like before. So we have PP and VP, and now to do language model integration, you have to augment the state of these nodes by the two boundary words in the English translation. That is, I not only need to know that this is a PP spanning for the Chinese phrase 与沙龙, but also I need to know that the translation starts with a with and ends with a Sharon. Similarly, held a talk, I need to remember the boundary words that is held talk. And then when you combine this PP with this VP, you do the reordering so that it becomes held talk with Sharon. And then the contiguous boundary words, so because when you combine them, the boundary words become contiguous, and then you score the bigram probabilities or bigram score So it's not only just the cost of or score of this plus the score of this, but also plus the bigram cost of talk width, right? So you have a probability like a width given talk or something like that. And this is called a combination cost. And that's the additional thing that is not existent in translation model only decoding. So after you score this, you forget this and only keep track of 2 boundary words for one node. So you always keep the 2 boundary words. And then later on, when you combine this VP with something here in MP, you combine the held with the boundary words here. So basically, when you combine things, you forget the middle, you score the contiguous boundary words, and then you always keep track of 2 words. Right. Questions? Another example, this is, so you got held talk with Sharon. Another example, you can have with Prime Minister Sharon, and still this is equivalent to PP spanning from Yu Xiaolong, but with Sharon as the boundary words. So whatever you have in the middle, I don't care, because for language model combination with other, like for future, when you combine this PP with some other item, you don't care what's in the middle here, because the only thing that need to be scored is the words on the boundaries. So with Israeli Prime Minister Sharon or with Prime Minister Sharon is the same amounts of equivalent items.
I can't remember whether you mentioned that. You only need the
2 boundary words.
The 2 words if you're using a bigram. Like
yes, exactly. If you're a trigram, you need to remember 2 words. So basically, yeah, that will be shown in the next slide. So held long meeting is same as held meeting. And then you combine them, you score the bigram pair meeting with, right? Because meeting. Mark?
Yeah, just a quick question.
Sure.
So, if you're doing argmax decoding,
Yeah.
right, wouldn't you keep track of the most likely string for each of these things?
The most likely string is just like you don't need actually you don't need that. You can do backtrack to recover that. Just
okay, but I mean okay.
Yeah.
But then you could actually use an arbitrary length anywhere.
Yes. So this is actually not inside the state. So this information that is inside the state is only inside this box.
But Mark, if you were doing argmax decoding and you remember the whole thing, it wouldn't give you the exact computation when you apply the longer n-gram score, right? Because what might be the argmax or one phrase with 2 words, the 2 particular n words might not still be the argmax when you scored it with
right. So that's why
longer context.
Right. So that's why with n-gram models, our states become more complicated, right? So they have more information in it. So previously, the 2 states that are equivalent are now probably not equivalent when you consider the boundary words also in the state. So basically, the dynamic programming states, the space becomes much, much larger with this kind of representation. But that's the only correct dynamic programming way to do it, to ensure that you get read the global one best with the additional language model. Okay, so why is that bad? Well, for translation model only, the complexity, the computational time complexity, is same as parsing, as I just said before. So it's linear to the size of the parsed forest or packed forest, which is cubic, because there are only 3 free indices, that is I, j, k, that is the indices on the foreign input. So you can vary I, j, k, whatever. So there's n is the length of the sentence, input sentence, so it's cubic, just as CKY or whatever parsing algorithms. When you have language models, you remember, you augment each of these states with the boundary words. But now for general m-gram model, you need to remember m-1 boundary words at each side. Because when you combine these 2 guys, you score this guy given these 2 guys and this guy given these 2 guys, right? So you have to remember m-1 at each side, right? So each state have two sides. Both of them is m-1 words. And you combine, you have 2, so you have 4 m-1. So that's why you have 4 to the power of 4 m-1. And the t is the target side or English side of vocabulary. So like this can range over all English words. That is the worst case complexity. But assuming you have only a constant number of translations, constant number of English translations per Chinese word, so that the choice of this guy, each of these guys can only range over n, which is a more reasonable assumption, then this still amounts to n to the 7 for bigram and n to the 11 for trigram, which is prohibitively large. And so in practice, if you really want to do full integration, you have to use with very heavy, like histogram pruning. And that's what our community really do in practice. But we'll develop more principled ways of pruning that is more efficiently searching over the space without detrimental effect on the search quality. That is, we want to have a good trade-off between quality and speed. Okay, so any questions for this part? Good. So the first technique is called cube pruning. So remember that full integration, it augments each node like this. That is a VP spanning for whatever Chinese string, all the possible LLM instantiations, and we call each of them an plus LLM item. So basically, this node can be augmented to like held talk or held conference or had talk or did talks or did talk or whatever. You have a lot of different LLM instantiations when you have language models, right? So full integration, well, in theory, computes all LLM items for each node, and that would be a huge number. But intuitively speaking, only very few of them would contribute to the one best derivation of the top node, right? And also in practice, almost everybody in statistical MT uses histogram pruning. That is to say, I only keep the top k, say k is 10, the top 10 plus LLM items, and I prune away all these bad items in the intermediate stages. And that technique greatly reduces the search space so that it becomes more tractable in practice, but it's still pretty expensive when you combine this PP with VP to form this bigger VP. Each of them has k LLM items, and you have, in principle, k-square possibilities to consider. Then you also choose the top k in this grid, right? And things become worse if you have, actually, in the real case, you have different ways to derive this node, right? So just like in CKY, you have different splits, and you have different rules. So you have a lot of different ways to derive this MP, and each of them has a square, because k by k, to start with. So the naive method of full integration would compute every square, the whole thing on every square, and then choose the top k among all the squares, right? And that's really bad because we just want the top k of this node in pruning, right? So can we do something like a little bit smarter than the naive thing? That is the cube pruning. So it's built upon the idea of k-best parsing. So we're going to see here. So this is a case of one hyperedge. Sorry, I should mention that each of this combination is called a hyperedge because this search space is of a hypergraph structure. So if you don't like hypergraph, it's just like a packed forest. So if we just look at one hyperedge, just like this grid, and this is like using PP and VP to form this VP, and say k is 3, and you have top 3 here and top 3 for this VP. And if they're sorted, because when you're pruning, I assume you sort them so that you get sorted order, and you have this grid. So the thing that after the plus sign are the language model combination costs, right? So for example, meeting along is really not like English, so you got the huge language model cost, and stuff like talk with is pretty good, meeting with pretty good, conference with pretty good, stuff like that. And so that now you want the top k out of this grid, right? So the question is, can you somehow avoid enumerating all these 9 cells and then get the top 3? Can you do something quicker than that? Well, if there's no language model cost, there's no such kind of plus something, then yes, because if you keep these guys, the column and the row sorted, then you know that this grid is monotonic. And the best one, the smallest number in this grid, must be the top left corner. So, and then the second best must be either this or this, right? So basically, you keep a frontier of the candidates. That is the candidate for the next best. And then each time you extract the best of them, say this guy 4.0, and push the 2 successors, right? So, and after this step, you already got 3 guys, and you don't even need to explore anything down here to save a lot of time, right? And this is using the algorithm 1 that I talked last year in k-best parsing. Any questions? So the general, just write a picture here, is like you always have a frontier, and you have the best one, extract the best one, and push the 2 successors. So, and the frontier gets like this in the next iteration. So basically, you just kind of have a water flooding kind of thing. You just the water flooding from here, which is the source, and just gradually floods the monotonic space. But okay, so this is even true across different hyperedges. So the real power of this k-best algorithm comes when you have a lot of different ways to derive this, and you don't need to get the k-best out of each square sequentially. You can do it in parallel, so that you still have a frontier that is all these blue guys. Or is this blue? Because I'm colorblind, so I don't know which color. And oh, it's purple and blue, yeah. And you can stop here because you already know that the top 4 across all these different across all these different grids are this guy and with these 3 guys, so that you even don't need to explore all these white guys, left them unexplored. So this gives a great saving of computation in k-best parsing. But the question is that we have this little combination cost here, which is language model cost. And with these costs, things become no longer monotonic, right? Because something that you think are good, like this 3.0, when they combine with this guy, it becomes very bad because this is the combination is something that you cannot predict, right? So you find that meeting alone is really like ridiculous. So you have a ridiculous cost. And so if you take the sum, that is the true cost, you find that maybe this guy is even better than this guy, and probably this guy is better than this guy, which is not really monotonic, right? But it's roughly speaking still has a little bit monotonic structure because these guys are monotonic. It's just like a little bit shifted so that it becomes a little bit like this, and so we can still do approximation of the top k using the same method before, but we prioritize the candidates using the true costs, right? So the first guy we still think maybe it's like this, and push the 2 successors, and this guy is the best, and push these 2, and now this is the best of these candidates, and push this. Now we get these 3 guys, but they are kind of out of order because we first explored this, and actually the second thing is better than the first guy. So that is different from k-best parsing because k-best parsing is always monotonic. You don't need to have this kind of different order. So the way to solve it, we have just a buffer to keep all the guys that you have already popped up. And when you accumulate the k guys, you resort them, and so that when you output the sorted list that is back in order. So this is, of course, approximation. So it doesn't. It sometimes have search errors because probably maybe this guy is really good and this has an obstacle very high so that you never visit this guy. But in practice, we're going to see it works pretty well. And we also see that with language model, the top 3 guys are these 3 guys. But without the language model, we remember that they get different shape, right? Because language model changes the space, the shape of the space, so that in our method, we prioritize the cells using the true costs that is sensitive to the language model also. So we not just do this kind of thing. We change. We do this, but the order of cells are having the language models into consideration already. Any questions?
So how do you put the language model?
Sorry. So this plus something is the language model combination cost.
Yeah. So what? But
it's no longer an optimal search.
Right, but you just said that you somehow actually incorporated the language model score into the order in which you...
Yeah, so you search over this space, that is the combined cost.
Right.
Right, and this space is no longer monotonic. Right, you can actually search over the previous the left number and that space.
Sorry, no, I just wondered if you were doing something like looking at the words on the edges and sort of saying, well, gee, actually, you know, maybe a long doesn't like to combine
with meeting.
A long has a very low unigram score, or bigram score.
Yeah.
So in fact, actually, I'm just kind of pushing it down. Yeah.
Exactly. That's a very clever technique, and that is used in our experiments, but we didn't talk about that in this talk. Because so we actually have a unigram, or if you have trigram, you have bigram also for this the left word, so that if you produce some really rare word, you know that it's gonna be very bad in combination, and you move that like to the right. So that,
that's what I thought you said.
Yeah, and that is very significant improvement in the performance. But yeah, and it's used in the real experiments. But here we just present the high level main idea. Okay. So the second technique, which is built upon Q-pruning and even faster, is called lazy Q-pruning. Because Q-pruning, if you remember, computes a fixed amount, like say top k, of LM items for each node. And this scheme can be considered as an on-the-fly rescoring. So pure rescoring just gets the n best list for the top node and then rescores using the language model. But this Q-pruning is like rescoring at each individual subtree, each individual nodes on the fly, so that each individual nodes, the k-best list, the top k, are sensitive to the language model. So the top k at each node is already a combined top k. Right? That's why it's called on-the-fly rescoring. But the question is, why not lazier, right? Because why don't you compute a fixed amount, an arbitrary k of LM items for each node? Why don't you let k automatically vary for each node? So for some nodes which are more ambiguous, you let k be larger, and for some nodes are really clear, they just need very small k. So our goal is to compute as few LM items as needed for the one best derivation of the top node. And to do that, we need a lazier version of the k-best algorithm presented before in Q-pruning, and that is the algorithm 3, because the Q-pruning uses algorithm 2, and we use algorithm 3, which is even lazier algorithm. We'll see in the next slide. So basically, if you put these 4 methods in one line, and Q-pruning can be thought of as a compromise between rescoring and full integration, and lazy Q-pruning is even more on the rescoring. It's even faster. Okay, so to do it lazily, we changed actually pretty dramatically the order of computation. So basically, after the first pass is the translation model only decoding. You produce a packed forest, right? And then lazy Q-pruning works backwards from the top node. So, for example, you have this kind of parse forest. Actually, this is not a parse forest. It's just showing one parse. To solve this top node, the one best LM item for the top node, you recursively say, okay, what's your best LM item? And this guy has to invoke subproblems. So what's your one best and what's your one best? And this guy also calls the subproblems, what's your one best and what's your one best? And after these little guys get their respective one bests, then you combine and to figure out the one best for these nodes. So this is the general picture that is recursively top-down backwards for the second pass. Now, suppose we're dealing with this VP node and using the 2 antecedents just as before, and we want to compute the one best for this node. But the question that is different from Q-pruning is that now we don't even know the one best of these 2 little problems yet. In Q-pruning, we are doing backwards, we're doing forward, bottom up, so that we always have the top k for smaller nodes. So we have top k here, before we compute anything bigger, right? Now we are backwards, so we're going to recursively invoke the same question like, what's your one best and what's your one best? So you call these two recursive calls. And after that, so after some recursion, it figures out their respective one best. So it says, oh, my one best is with Sharon, and my one best is held meeting. But now, so now you know the top left corner, right? So at least you know one derivation for this bigger VP node. But can you claim right now that this 2.5 is the best in this grid? Well, if it's k-best parsing, then fine, because it's monotonic. But now, because later items, although worse than this, but they probably are better in combination, which you cannot predict, because there's a language model cost, combination cost, which causes non-monotonicity, which you don't know yet. And in fact, this node is actually better than this, right? So what we do, we're gonna wait to see more variations. So basically, we're gonna solve the second best of this PP node and the second best of this, and to see if the second best gives you some better things in combination, right? So we do the recursion and we solve these two subproblems, and now you can compute these two guys. Actually, you find something even better, right? And you continue this until you're confident that you've already found your one best. And then you can stop the recursion and report to the parent node that I already know my one best. But the question is, when are you confident that the current best that you got will not be surpassed in the future, right? So when you only have 2.5, there's actually a possibility that something is even better in the future. But here, when you have 2.4, can you say that 2.4 will not be surpassed in the future? Well, that is the problem of estimating how well the future would be. And the only thing we know that the future is that if you have no language model, then you always get worse and worse. That is what we already know. But with language model, it's a little bit non-monotonic. But what if you have a lower bound that is the lowest number of language model combination cost in this hyperred that is on this grid? Then by replacing the combination cost with this lower bound, say lower bound is 0.1, then you have the BLEU numbers, which is the heuristic of X. And then this BLEU numbers, if you look at it, is still monotonic, because this is like just this guy plus this guy and plus a constant for this grid. So it's still monotonic. And the BLEU number is actually a lower bound on anything that is in the future that is to the right and to the lower and the right of this grid. So for example, at this stage, you have these two guys in the candidates. And this 4.1 says stuff that in this region might be as good as 4.1, but not anything better than 4.1, right? Because of the monotonicity. And this guy says stuff in this region will be probably as good as 2.2, but no better than that. So if you take the minimum of the heuristic of X in these candidates, which is 2.2, then you know this is the lower bound of anything that is yet to be explored. So it's the lower bound of the best true cost in the future. And this is a theorem that we can prove rigorously. Any questions?
Where did you get your estimate from?
Yeah, that's a separate question that we're going to get separately. Yeah. But suppose we have a magic procedure that gives us a lower bound. Then this is like a heuristic in A star, which is the estimate, which is optimistic estimate of the future. So the point of estimates are always they must be optimistic. In A star terminology, it's admissible, so that you don't have search errors. Otherwise, you will have search errors if you're not exactly optimistic estimates. Now, okay. Now, so when you have 2.5, you compare 2.5 with the best BLEU number in the candidates, and now the 2.2. So it says that I still have the potential to be 2.2 or 2.3 or 2.4, so that you cannot claim 2.5 is my best at this point, right? Because this guy says I still have this potential to be better than you. But next step, when you already enumerated this 2.4, and the candidates are these three guys, and the minimum of them 4.1 says that anything here in explored can be no better than 4.1. And then you are sure that these two guys, 2.4 and 2.5, are really my one best and second best. Then they will not be surpassed in the future anyhow. So we can stop recursion at this moment and report them in order so that we got 2.4 and 2.5 as my one best and second best. Any questions? Okay. So comes to the question that Arun asked, estimating the combination heuristic. So to get a true lower bound, this is not easy. You have to do a similar method to full integration, and it's still a little bit slow in practice. I mean, like estimating heuristics in A-star parsing is also, in A-star methods, also sometimes a problem by itself, because if you want to be very accurate, you have a lot of pre-computation time invested in it, and sometimes it's not worth it because pre-computation already gets you some very slow method. So in practice, we use something much simpler instead. So we only use the k-best translations from TM-only decoding. So we, like rescoring, we get the top sound TM-only translations and estimate lower bounds just within these k-best translations for each hyperedge. Each hyperedge meaning each combination like VP13 combined with PP36, so that we can estimate lower bounds for each of them inside these k-best translations. And this is just an approximation of the whole translation. So this is just an approximation, and it's no longer guaranteed to be a true lower bound. So it's not really admissible truly, but it's like almost admissible when your k is getting larger and larger, and when your k gets to infinity, it's really admissible. So it's like almost admissible heuristic in A-star.
Are you going to say more about this?
No.
Because can you just say then, so what is it? So we get the k-best translations
Sure.
from using the translation model.
Only, yeah, not taking language model into account.
Okay.
Yeah.
Right, now, so now what do you do? So now you estimate.
Yeah, estimate. So the so suppose we get using translation model only, we get this kind of structure, and then we estimate for each hyperedge, that is for each this kind of combination, we estimate the language model combination, because translation model only already gives you a translation. So this is the translation for MP, the translation for VP, the translation for PP, and you can score the language model cost in this translation because you have a structure, right? And this is one possible value for the LM combo of these two guys, right? And in another derivation, might produce a different translation like this, and a different translation for this PP, and you score this, and you take the best, take the minimum of all these different ways of doing the same combination. So, I mean, in the second best TM-only translation, you got something different for VP and something different for PP.
So does that mean that you're using the same language model heuristic cost for all the cells and those tables that we saw before?
No, only for each unique hyperedge, meaning.
Yeah, that's what I mean.
Each hyperedge corresponds to one of those k by k tables.
Exactly.
So you're basically computing the language model score for all the boxes in the table.
Yes.
And you're using the lowest value
Yeah.
as the heuristic.
Yes. Yes. So
You could use the lowest value. You could have a separate heuristic for each column and row, right?
He's not doing it for each box, right? I mean, he's doing it once, right? He's doing it. I mean, if you go back to the previous.
No, it's for each.
He has to
each
compute
box.
all the boxes to pick the lowest one.
You may be looking at using the word box differently.
Okay.
For each of them,
Yeah.
for each grid,
For each grid has a
he's
separate.
computing a single.
Yes.
Yeah.
But
No,
he has to
Exactly.
compute the actual value of the LM for every square in that grid to get the minimum
No,
across there.
well, he should.
Not for his
but he doesn't.
estimator.
But he
Not
doesn't.
for his
For his
estimator.
estimator, he doesn't.
For the upper one, for the one in black, yes, not for the one in blue.
Yeah, for the one in blue, what he's going to do is he's going to say, okay, I know what the translation model on its own would do. You know what, which phrases it would pick for those, for the VP and for the PP. Okay, I know what it is. I'm just going to, and then I'm just going to score that in the language model, and I'm going to use that as my H of X for all the cells.
Yeah.
But he does that minimizing over each of the n best
Yeah.
using the translation model alone.
Does that minimize it?
So for each hyperedge, you
Yes.
take k-squared distinct combinations
No, no,
and
no,
look at
no.
the language model
No.
contribution score?
No.
Because aren't there,
That would be
didn't you take k-best from the translation model?
Yeah. So the k-best from the translation model say this is my one best according to translation model, and produce something like.
So you have k translations for the VP and k translations
No,
for the VP?
k translation only for the top node.
Okay.
It's for the global
Yeah,
problem.
so there's just one translation there.
So in that
it's one.
case, if, so
Well, the k-best translations for the top node might involve anything up to k translations from any lower.
Exactly,
Yes.
but maybe much less than that.
but much less than k squared.
Yeah, much less than k squared. Yeah, definitely.
Yeah.
So
Yeah.
I say this compared to this and take the best one to be the heuristic of this hyperedge. And this is a constant number for one grid, right? Because
Right.
one grid is one hyperedge. And in the top sound translations for the top node, you probably only see this hyperedge 3 times or once or even say twice, right, for this kind of combination. But the intuition is that more important hyperedges got more accurate because it's represented more in the k-best translation. So it got more accurate, more admissible heuristics. And for those who represent only once, probably it's very risky.
So you can probably tell actually how bad, how often this heuristic, in fact, actually turns out to be too pessimistic,
Uh-huh.
right?
Do you have an empirical survey of how often one of the scores in the grid goes below the...
Yeah.
So
When,
was it-
yeah. When we do this, yeah, I used to have a statistics like when it really becomes less than the one that you estimated, it gives you a warning that yeah. So, but I don't have a overall statistical how often that.
It's pretty rarely.
Yeah, not causing much problem. Actually, the other way we look at this problem is, does it really cause search errors? So probably you got something that is even better than your heuristic, but it doesn't affect the search quality for the top node. That's likely to be the case. Okay. So important hyperedges have more accurate estimates. And okay, let's look at experiments. And the current experiment we run on is on top of a tree-to-string, or called syntax-derived system that I built from English to Chinese. So the rules look like this. So because we're translating from English to Chinese, we first parse the English sentence to a parse tree, and we pattern match the English parse tree by rules like this, which says if you want to translate a passive construction, that is was somehow, which is a VBN, by somebody, which is NPC, then on the Chinese side it's by somebody somehow. So if a subtree, parse tree on the English side matches this rule, then you convert it recursively to the Chinese order here. And you recursively solve these two subproblems by pattern matching with smaller rules. And formally speaking, this is a synchronous tree substitution grammars. It's not a synchronous context free grammar because we have more than one level here, right? So it's a little bit more than synchronous context free grammar, but the derivation structure is still context free, so the algorithm still applies. And in practice, it's slightly better in our test set in BLEU than Faro. And this is our experiment trained on 28 million words and tested on 140 sentences. So this kind of plot is a trade-off between search space measured by the number of LM items per sentence and the model cost. So we prefer lower model cost, right? So our goal is to get to somewhere. The best thing is to somewhere here that is you're very fast. You explore very few items, but you still got a pretty good model cost. And the worst case is somewhere here that is very slow and you got not suboptimal.
So model cost is what the score,
The score-
optimal
Of the one best you found.
That's right, but the TM and the LM.
TM and LM. Yeah.
After search, right?
After
so,
search.
So we're trying to minimize that.
You minimize that, yeah. You prefer to push to this origin, right? So this red one is full integration. So it's going to be pretty slow when you want to pretty good quality, right? And this is cube pruning. The blue one is lazy cube pruning. So like for same level of search quality, like if you draw some horizontal line here, we're going to see that lazy cube pruning is faster than cube pruning, and cube pruning is much faster than full integration, especially when you have a line here, which is the optimal performance. And this is lazy cube is like 40% of cube, and cube is and 40% of cube, and also about 7% of the full integration. That is the reduction of search space. Or if you draw a vertical line here, that is with the same amount of time, so I only allow you for, say, 1 second per sentence, how well your search quality will be. And similar story is that with the same level of search speed, lazy cube pruning produce better translations than cube pruning. Cube pruning is better than full integration. So this kind of plot is like a comparison, is a fair comparison with the trade-off, Chris.
So the y-axis is perplexity, or?
No, the y-axis is model cost. Is that a combined
model cost like neg log likelihood?
Negative log likelihood, negative log probability.
Can you tell me something about what the difference between 218.8 and 218.2 is? I mean,
Why are they so close?
It's very close, but
that could be a significant difference. Like,
yeah, that could be a significant. The translation will be very different. Although the score, I mean, the top 10 translation will have all very close scores, but they got to be different.
Do the translations look qualitatively very different from the top to the bottom?
Qualitatively, meaning in terms
they
of
have
blue.
Different words in them.
Yeah, they have very different words in them. Yeah. So the first best and second best have maybe 1 or 2 words different, but yeah. So although it is very very close, but yeah, the translations are very different. Or would you have the same question? Okay. Okay. And this plot is replacing the y-axis with blue score and the same x-axis as search space. So the higher the better. So we're gonna push to this direction. And here you see that also the same story, that the lazy cube pruning is better search than cube pruning than the full integration. And the blue score range is not that high. Chris?
Well, you took a lot of time running the full integration. It looks like you still have more headroom with cube pruning and lazy cube pruning, though. I mean, if you kept giving them more time, would the scores keep rising?
Not really. It's like converging after this. So
Okay.
yeah. But yeah, if you can stop here, it's pretty great. And this is like definitely just convergent here. Okay, so this plot is the search space versus the number of nodes in the forest, or like the size of the forest, which is in our model it's roughly linear to the length of the input sentence. So just to see how well these three methods scale for different lengths of sentences. So full integration is like very high, and cube pruning is roughly linear, and lazy cube pruning is also linear or maybe even a little bit sublinear, but with a smaller slope, with like half or more than half the slope of cube pruning. So basically we can see that they are much faster than like full integration here.
Of course, I mean, the full integration model has presumably got the cheapest cost time per node explored, right? I mean, the lazy cube pruning's got a fairly complicated process where you calculate these heuristics to work out which nodes you really want to explore.
Right.
They all go along to priority queues.
Yeah, but this is.
I'd say, yeah, I mean, factor of 10 is still a factor of 10, but.
Yeah.
But in terms of times,
in terms of time, there's a little bit overhead, yeah, but
not much.
Not much, yeah. Like this kind of plots, if you replace with the time, I mean wall clock time, instead of the number of LM items, this blue curve will be a little bit closer to cube pruning because there's a little bit more machinery there. But the difference between this and this is always very significant, yeah, because this is like huge difference. And yeah.
I mean, it still is only a factor of 4, right? I
It's
mean, that's not a.
That's
not a logarithmic.
Right.
Scale.
Right. Yeah. Because full integration is also with heavy pruning, so it's not like.
If we go on to the next graph, Do you have any intuition why full integration isn't doing as well as the pruning algorithms? You know, even when you give it
infinite amount of time, or
Because he says he's doing a lot of pruning there.
yeah.
But if we go back, right,
The model cost is similar.
the model costs are very similar, right?
The model cost is very similar, but actually these two, the top two dots, is somewhere not shown here.
Oh, I see. Right. So you
like
say you're going further down.
right, further down here. If you compare these three dots, they're about the same quality. These three dots, I mean, yeah. But to let this guy extend, there will be like infinite time maybe here, and yeah, these guys are still like this kind of.
So that difference is only a few hundreds of a BLEU.
Yeah, that is because our test set is relatively short sentences, and yeah, the language model is also not trained on a huge text. It's just on the English. Oh, sorry, it's just on the Chinese side of the parallel text because we are translating into Chinese. Okay, so extensions or current or ongoing work. So we can apply the same story of Q-pruning, lazy Q-pruning to other problems, other search problems in NLP. Say for instance, lexicalized parsing. So we know that most of the state-of-the-art two-band parsers are lexicalized, like Collins and ChiangYang's parsers, and the probability is conditioned on the lexical heads. But that is to say, we annotate the non-terminal set using the lexical heads, and that results in a huge grammar, which everybody knows it's a very heavy grammar constant in parsing. So people have proposed multi-pass parsing, that is to first using a coarse-grained grammar, probably non-lexicalized, and then in the second pass add back in the lexical heads. Right? But in terms of cube and lazy cube pruning, if we apply this technique with the multi-pass, actually lazy cube pruning, actually both of them assumes that there's two separate passes, right? So the first pass is just unlexicalized parsing, and according to ChiangYang's data, it's like 77 F score, and the fully lexicalized we know it's like 88 or 89% F score. And the second pass is that you can view the lexical probabilities as the language model combination costs, which is causing the same problem of non-monotonicity, right? So that's the analogy between lexicalized parsing and machine translation with language models. And the goal is, hopefully, we can be almost as fast as unlexicalized parsing, because you know the k-best, even we have the k very large k, because the k-best algorithm is very fast, so it won't be much slower as the unlexicalized parsing. But our goal is to be almost as accurate as bilexical parsing as the standard ChiangYang and Collins parsers. Another viewpoint, another perspective is that this is the story that we usually do, that we have an input and we have a complicated model, so we break them into simple model and a complex model. And simple model is fast, so we produce an best list. And then you re-rank or rescore the best list with the complicated part, and you get approximate the global one best. And what we, so what ChiangYang and Johnson do for the coarse-to-fine grain and best parsing is you have input in a simple model and you produce a small packed forest, and then complicated model and big forest. That is by splitting the small forest, the states in the small forest into several fine-grained states. And then in this paper, the goal is to find the k-best in this big forest. Is that right? Okay. So our work is that you still have the same first pass, a small forest, and you can prune the forest actually, like what you guys did. But the complicated model works only on the small forest, like doing the k-best on the small forest, but the k-best is sensitive to the combined cost. That is, the k-best, like in our work, is the k-best of language model combined with translation model. So it's not, first of all, it's not anything producing this big forest in the first place, but it's not like this, which is only re-ranking on this best list. So it's roughly, as I said, it's on-the-fly re-ranking, and probably can be called forest re-ranking using the cube and lazy cube k-best methods. and you get the goal is to get approximate the one best out of this complicated model. So to conclude, we present two techniques based on K-best algorithm for fast decoding in machine translation, and we achieved pretty good speed quality trade-off. And this method can be generalized to be a generic tool for reducing the complicated search space in a lot of problems in NLP. So it can be viewed as on-the-fly forest reranking, and it can be probably a generic tool as an alternative to A-star kind of thing, A-star kind of methods. But our goal is to not aim at the global optimal answer, but by approximation, achieving good quality and speed trade-off. And the motivation is that fast decoding can also help learning in discriminant training like perceptron-style algorithms, so that in the long term, we're going to investigate discriminative parsing and translation methods using lazy cube pruning and cube pruning, so that because we know that in constituent parsing, for example, still the generative model is the best. I mean, in dependency parsing, Ryan McDonald's work showing that discriminant training with faster decoding methods can be very helpful, but not in constituent parsing. So, and also in machine translation, we're going to explore these directions with this faster decoding as a black box, so that our future work can just depend on this fast decoding algorithm. And this is it. That's